after collision. And then again, obviously, for your momentum, we work with your velocities and mass. That's the product. For them is momentum actually, and they have the unit kg meters per second. And again, the idea that a momentum is a vector quantity mainly because it has a velocity, right? The velocity is an upper hand. That's why it has it is a vector quantity over here. So now, with all these things stated, we're going to start with this one. First question over here says that which of the following quantities is the SI unit for kg meter square per second? And it was not quite related to momentum, but it's quite easy. Which one do you think is the correct SI unit for this unit? I mean, uh, yeah, SI unit for this base unit. Which one is the formula?
Work done.
Work done. 1 minute. Force is kg meters per second. Momentum is this. Power is, um, yeah, energy, right? Yeah, energy is your answer. Wait, is it energy? 1 minute. We have a S power 3 over here, right? So if you use your like just energy, energy is going to be your, let's say, mgh, right? That's your kg meters per second square times meter. So you actually get kg meter square over second square. That's your energy. That's your energy or work done. When you divide this with time, you get power, and which is your kg meter square is power minus 3. So answer should be power, not work done. Is this clear?
Yes, teacher, clear.
Okay. Then for this one again, the trolleys X and Y are, say 1 minute, trolleys X and Y of masses m and 3m respectively are traveling in the same speed. They both have the same speed, but their one thing to focus is that they have different masses, right? Y has 3 times the mass of what X have, and the trolleys collide and move off together. And I need to identify that which of the following statement is correct in this case. Acha, okay. For this one to identify which one over here have the correct statement, I they're saying that force of x on y during the collision is greater than the force of y on x. Actually, I mean, in order to create the same momentum, right? Because they are moving in opposite direction after the collision also, the momentum has to be balanced. In order to create the same momentum, since like y is already heavier, x is less heavier, the force of x on y in the collision is greater than the force of y on x. Yeah, no, this is wrong because this one is already at a heavier mass, right? So during the collision, during that, I mean, again, no one is actually going to exert a more force or less force in each other, because for momentum, in order to be balanced, we don't talk about force, we talk about their masses, right? So they are going to exert equal forces on each other, but because y have a bigger mass, it will maybe like reverse its direction and have a smaller velocity. And because x has a smaller mass, it could also reverse its direction, but by magnitude wise, x should have a bigger velocity than y, because then only the total momentum will be balanced, right? So force is always same. It's not a matter of force. For your momentum, by the way, they follow your Newton's third law, right? They both exert equal and opposite force over here. So equal and opposite force in this case. If they're going to exert equal and opposite force, then obviously that's your case for what? Equal and opposite force indicates that they're not exerting different forces on each other. They're both exerting same forces on each other. That's why this is not a correct answer. This is also not a correct answer. Again, they're saying that maybe y is exerting more force on x than x is exerting on y, right? That is wrong again. No one is exerting more force. Everyone is exerting equal force. The speed of x after the collision is greater than v. Um, the speed of x after the collision is greater than v, and the speed of x after the collision is less than v. Okay, first thing to understand, the trolleys collide and move off together over here, right? Since after the collision they're going to combine and move off in the same direction, right? Don't you think that in this case, after the collision, since this one already have a like what bigger mass, right? So even if you apply like same amount of force on x and y, that force will have a smaller effect on y and bigger effect on x because y have a bigger mass. So that's why even if I'm providing 5 Newton on y, maybe that will not be able to reverse its direction. It will be able to like make this what where is my cursor? Okay, it will be able to sorry, 1 minute. Like if I apply 5 Newton on both the trolleys over here during collision, but this 5 Newton will only make the trolley Y to decelerate, okay, because the mass is very big over here. But for this one, the 5 Newton that is provided on X, because the mass is small, that 5 Newton is able to transverse, like, rotate its direction of motion and eventually have a smaller value, right? So you can write that after the collision, what is happening? After the collision, mostly this is supposed to happen. This is 3m, y, and this is m. After the collision, m or that trolley x have reversed its direction, and y continue to move in the same direction but at a lower velocity. Okay, like lower velocity compared to whatever you had previously. Now, they are saying that the speed of x after the collision is greater than v. The speed of x after the collision is less than v. Now, what happens? Again, before collision, your momentum had something, right? After collision also, it needs to balance that. That means what? Obviously, the speed of x after the collision should be less than v in this case. Why less than? Because it's reversing its direction. You can see that, right? So your final velocity is always going to be less than to whatever you started with. So their direction is also changed. But since you're talking about speed, which is basically the magnitude of the velocity, that's why direction is not a matter for you. Only idea is that after the collision, the speed of particle x is going to be smaller than whatever it had originally, v value. So it's going to be b over here. Is this clear?
Yes, teacher, clear.
Okay, then over here, if you move, we didn't actually had that much MCQs from here actually. Yeah, we didn't actually have that much MCQs. So we'll move on to your detailed questions over here. So now this one I can see, state the principle of conservation of momentum. So before and after collision is given. Before collision, I can see that asteroid a slow moving asteroid A was moving in this direction, and there was a faster moving asteroid was also moving in the same direction as asteroid B, and eventually they collided, right? And after the collision, this is how they look. After the collision, the asteroid A is absorbed by sorry asteroid B is absorbed by A, so A and B kind of combine together, and then they move in the direction of A with a combined velocity. So first thing we're asking, principle of conservation of momentum. This is obviously a repeated question, right? It says that total momentum before and after collision should be equal, provided that no external force acts onto the system. Total momentum before and after the collision is equal. Acts onto the system, right? So then again, after this, before the collision, asteroid A has velocity of this much and a momentum of this much. Show that the mass of asteroid A was about this much kg. Okay, 1 minute. Before the collision, A has velocity of this and momentum of this. Mass of asteroid. Oh, yeah, I have the velocity, right? So I can easily find the mass. So your momentum over velocity, that's going to be 1.8 times 10 to the power of 17 over 2.19 10 to the power of 3. How much is this? Amir, can you please calculate this for me?
Okay, teacher. 8.21 into 10 to the power 13.
8.21 in a little bit then, okay. 8.219 something, right?
Yes, teacher.
So we'll write 8.22 10 to the power of 13 kg. That's your final answer. Okay, then after this, they're asking that now calculate the velocity of the asteroids after the collision. Asteroid B has a mass of this, and velocity of the asteroid B before the collision was this, right? So I understand the formula is over here is going to be this, right? Basic thing is that total momentum before collision is equals to your total momentum after collision. For before collision, you have your mass of A, velocity of, sorry, initial velocity of A, and then again your mass of B, initial velocity of B, mass of A plus mass of B with some final velocity that you're going to get, right? So from there, you just make V the subject. Now, momentum of what did you calculate it previously? This was for A before the collision, no? Where the momentum was given as 1.8 10 to the power of minus positive 17. So I can write that 1.8 10 to the power of 17, the total momentum of A is given. For total momentum of B, we have to find the momentum as 5.9 10 to the power of 12 times 15 10 to the power of 3. And then we are going to divide this with your how much? Divide this with your, what is this? The combination of their masses, right? Previously, you got the mass of your asteroid A, which was 822 10 to the power of 13. So you get that 822 10 power 13 plus your mass of asteroid B is 5.9 10 power 12, right? And when you calculate this, you'll get your answer. How much is this? How far have you finished the worksheet 4 from waves, Amir?
Sorry, teacher.
How far have you finished the worksheet 4 from waves?
Please, 1 second.
Sorry?
Worksheet 4, yeah?
Yeah, unit 2 waves. How far have you completed that?
I'm doing the MCQs. I think I'm done
Okay.
with it.
Okay, so almost 80% of worksheet 2 is left. Worksheet 2 from moment is left, and you are supposed to submit all of that by tomorrow.
Tomorrow?
Yeah. Today was the submission date for your worksheet 4 from Waves. I'll extend the time, but by tomorrow you have to submit. In that case, on tomorrow's class, we'll start with photoelectric effect, and I'll do the problem solving from worksheet 2 and 3 on Monday.
Okay, teacher.
Yeah, but you have to submit that by tomorrow night, okay?
Okay.
Okay, then how much do you get from this calculation, by the way? I asked you to calculate.
I got some error.
Alright, 1 minute. So maybe there was some problem with the brackets. 1.8 10 to the power of 17 plus first bracket inside that 5.9 10 to the power of 12, and then you have that multiplied with your 15 10 to the power of 3 bracket close, another bracket close, divided by your 8.22 10 to the power of uh, 13, and then I'm going to class this with your 5.9 12. No, we get like 3,400, say 3,047.6. That's approximately 3,048, or like you can write 3,050 over here.
Yeah.
Right, so you can write 3,050 meters per second. That's your velocity over here. So then this is right. After this, if you move on to your next one, this is a vector quantity. This is a vector diagram actually, not to be honest, a momentum. We're supposed to draw a vector diagram over here. So for this one, they're saying that P and Q are identical spheres. And over here, we can see that P moves along the smooth horizontal surface and collides with Q. Like before the collision, they were actually in the same plane, and Q was most probably stationary over here. Yeah, Q was initially stationary, and then P was moving towards Q, and it collided with Q, right? And after the collision, P moves off with the momentum of this much in a direction of 15 to the horizontal direction or initial position, and Q moves off with a momentum of this much at an angle of 10 degrees from the horizontal plane. And we need to draw a diagram for this, like use a scale diagram to show that the momentum of the total, like the magnitude of the total momentum of the spheres P and Q after the collision is about 0.2. Oh, like for your after collision, you're supposed to only do this, not for the initial collisions over here. Yeah, they're asking you that, after the collision, the total momentum for P and Q is like 0.2. You just have to show that from this diagram. So now first thing over here, this is what kind of a thing? This is actually a a vector diagram with two vector quantities acting, right? So what do you think? Should I draw a parallelogram or a triangle over here? Like what do you do over here in this kind of cases? Do you understand my question, Amir?
Mm,
So I was actually asking that, when we work with this kind of things, do we know how to draw a vector diagram, by the way?
I think I remember.
Hmm. Yeah, anything you remember, you can like tell so far. What do you think? How do you draw the vector diagrams?
We take the we take a unit now. We divide it. Then yeah.
No, no, you're explaining vector in maths. No, no, in physics, I actually explain it in a different approach. Okay, so I'll give you a small explanation for that. So, in what situations they ask you to draw a vector diagram. There are two situations. One is when the object is in equilibrium, okay, where all the forces are acting, but they all will cancel each other out somehow. And another is this kind of situation, where vector forces are acting and they do not cancel each other out. You have some resultant vector quantity at the end. So if you are working with objects who are at equilibrium, then you use the triangle method. But the triangle method you use in this way. For example, let's say a frame is hanging from like wall and all, right? So it has this tension obviously along the two cables. So if you have this tension, that means what? You can draw a free body diagram over here. Obviously weight is also there, right? This is your weight. um, because of the wires, the particle is hanging there, so obviously tension is acting in this direction, right? T1, T2, and weight. So I can arrange them and draw a triangle something like this. And this is going to be your T1, this is going to be your T2, and this is going to be your weight. You have to understand one thing, that in this rearrangement, I did not change any one angles over here. Now you can see T1 was upsloping, slightly tilted to the right hand side, or sorry, to the left hand side. You can still see the same approach over here, right? T2 is upsloping, slightly tilted to the left. And then again, T1 was upsloping, slightly tilted to the right. T1 upsloping, slightly tilted to the right. And weight was vertically downward, weight is vertically downward in my diagram also, right? So whenever you work with objects that are in equilibrium, all their forces will always create a triangle method. Is this clear?
Yes, teacher, clear.
And non-equilibrium state, like this one, where you have to find out like in which direction the resultant force will be, like forces are acting, or maybe vector quantities are acting and they're not equal, so you have some at the end resultant surplus vectors. So if you have to find that, how do you calculate that? You calculate that by using a parallelogram. Like over here, what was the situation? This is your object, right? And what was the angle in between them? 15 degrees from the horizontally above, 10 degrees horizontally below. That means in between them, like the final momentum of P and Q, have an angle difference of 25 degree. I can understand that. So if I move up and I have this is the momentum of your P and this is the momentum of your Q, right? Acha, then and then again in between them you have a 15-degree value. Acha, we'll talk about that a little bit later. So first thing, momentum, we're moving in this direction. In order to identify, in which direction the final resultant vector will be, I'll have to create a tip to tail diagram. Tip to tail means I'm going to copy this momentum of Q and connect it to the tip of your momentum of P, with the tip of your momentum P. And then again, I'm going to copy the momentum of P, duplicate this, and then connect it to the tip of your momentum from Q. Okay, and I can see that over here, what is happening from this one and from this one, all the arrows are kind of heading to this point, right? So this is your final point. This is your final point, and this is your origin, because this is where you started the journey from. So your final momentum is going to be somewhere like this. Not exactly a straight line, because I did not do a full scale diagram, but roughly this is how we identify the direction of your resultant vector. Is this clear? Amir, is this clear?
Yes, teacher.
Right, this one I name it as parallelogram method. Not I name it, in your book also the name is parallelogram method. Because you know how you created and copied the forces or vector quantities, like this was the momentum of P, and this was still the momentum. Yeah, momentum of P, and this is again the momentum of P copied version, right? And then again, this is a momentum of Q, and this is a momentum of Q copied version. Because of your copy pasting and connecting them together according to your tip to tail combination. Tip to tail means like how I take this one and connect the tail of your momentum of Q with the tip of your momentum of P, right? That's why we call it as a tip to tail combination also. Using this diagram and arrangement, I can then identify that your final vector quantity will follow along this way, how you can connect the origin to the final, right? And that will be the direction for your final vector quantity. So then again over here, if I have all these informations and I need to find the magnitude of your resultant vector, so I'm going to obviously plot a graph that has like equal lengths and everything. So first thing, the angle is a little bit problematic, your angle between P and Q was how much? 25 degree, right? Now you have to understand that if I extend Q, right, this angle was 25 degree, okay? This angle was 25. If this is 25, how much is this? You just subtract that from 180, so you kind of get like 165 or something, right? So you get this as 165, you know. You're not going to draw this directly on your scale diagram, but from there, you know, you can identify the shape of everything. So now if you have the angle between P and Q and everything is there, since I'm going to draw a scale diagram where the momentum of P and Q have to have a like you know constant ratio with the original value, and whatever the length I draw on my graph paper, they must have a constant ratio. I cannot just randomly put anything in the graph. So I have to do a scaling there. But before that, I need to pick that, you know, since I'm going to do scaling, so it's going to be very difficult to do scaling for four different lengths, right? So I just, you know, do the parallelogram to identify the direction, to identify the shape of the triangle. And then in my answer, I'm only going to choose one of the triangles and just draw that in my diagram, because, you know, I got a visual representation that how the diagram is supposed to be, but I do not need to draw the full parallelogram, right? I can just work with this portion of the triangle also. With that parallelogram, I have clearly found out my direction of the resultant vector. And now I can only focus on one section of the parallelogram. So in my graph, first thing I'm going to do, I have to do a scaling. Scaling is that momentum of your particle P after the collision was 0.096, 0.14, right? It's a very small value to represent on graph. So how can you represent them on graph? So I need to multiply something with them to make them at least, you know, little big so I can plot them on my graph paper. So if I have 0.14 times 10, I get 1.4. 0.096 times 10 is 0.96. That is still very small. I need to multiply, let's say, 0.14 times 100, right? Yeah. If I multiply 100, 0.096 times 100, I get 9.6. So I can write that your like 0.096 kg meters per second is going to be represented as 9.6 centimeter, and 0.14 kg meters per second, and that will be converted to your uh, 14 centimeter, you know. This length that I have calculated, I'm going to use that to plot in my graph. So now over here, what was the angle difference between them? 165, right? So I'm going to use my scale. This is exactly horizontal, and I know that if this is exactly horizontal, it's supposed to be like not tilted, something like this. 25 degrees. This is actually the angle for your particle Q, right? Particle Q was, or you know, you can actually use it in this way. Like you can just draw a horizontal plane, okay? And then from there you just start measuring the angle. Like this is your horizontal plane, okay? Particle Q was what? 10 degrees. Yeah, particle Q was 10 degrees below the horizontal plane. So 10 degrees below the horizontal plane means what? Something like this, right? 10 degrees below the horizontal plane. And now you need to draw a graph for, like line for 17, how much was that? 17. No, 1 minute. 14 centimeter, yeah, sorry, 14 centimeter. So yeah, I mean, I can draw that. Problem is, I don't actually have this much, like, you know, space over here. So just a minute. If I have 14, you know, I could have just multiplied them with 50. Okay, that way I will get enough length that is suitable for my given graph. So you can actually multiply any random values to your vector quantity to make them represent in a value that is more suitable for you to draw. Like over here, 9.6 and 14 will not fit on my PDF, right? That's why I'm multiplying them with 50 now instead. That will give me 4.8 and 7. These are smaller links, I can easily fit in my PDF. But for your graph paper, originally graph paper, you have to keep in mind that you have to use 70% of whatever area they give you, right? So I think for your graph paper, you will be able to use your, what was that, 14 centimeters or 9.6 centimeters. But since I'm working with a PDF, I can only give this much or get this much, right? Okay, now I have to draw a line for 1 unit, 2 unit, 3, 4, 5, 6, and then 7. I'm going to stop exactly over here. This is a 7 unit length. And then again, I'm going to make this increase 15 degrees, right? Exactly 15 degrees. And then plot a graph for 4.8 centimeters now. So this is your 0, 1, 2, 3, 4. 4.8 is exactly here. This is how the graph will look. And the horizontal line, by the way, you have at the bottom, that's only there to, measure their angle values, nothing else. Okay, you can just draw this as, since, this is not actually a part of your graph, this was just there to measure their angle values. You can actually draw them as a broken line indicating this is not a part of the graph. And this was 10 degrees. This was the momentum of your particle Q, and this was the momentum of your particle P. So this is Q and that one was P, and this is your, so this is 15 degrees, my mistake. This is 15 degrees, and this one's your 10 degrees. Now what am I supposed to do? I'm going to like connect your final points together, right? Them over here together, and I can use that length to find out the magnitude actually. This is how the line will be connected. Sorry, 1 minute. Right. And I can see that what is the length of this line? I have 1, 2, 3, 4. 1 minute, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 point. My mistake. Sorry, I cannot actually see properly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. This is where 11 ends. And then this is exactly at 12, by the way. For your scale, this is exactly at 12. I mean, I understand that you might not be able to see the reading on the scale, but this is exactly at 12 centimeter. Okay, 12 centimeter means what? For everything, I was multiplying 50 now. So if I have to get the final resultant vectors or this resultant velocity's magnitude, the length is 12 means I'm going to divide 50 with them and you get 0.24. So over here, this is your 0.24. Okay, kg meters per second. Another thing, by the way, when you draw this, obviously you're going to draw them with the length 4.8, 12 centimeters or 7 centimeter. But reading should be the magnitude of your vector quantity. That means over here, we're going to write 0.096 kg meters per second, right? I'll never write 4.8. Over here, I will write 0.14 kg meters per second. I will never write 7 over here. And then again, I also need to find out the angle. I can clearly see this is exactly horizontal, right? The vector quantity that I got is exactly horizontal. So it doesn't create any angle. It's entirely on the horizontal plane. That's why the question also did not, ask you to calculate or measure the value for your momentum over here. Now, one thing to understand, the question was saying your answer should be very close to 0.2. We got very close to 0.2, right? The answer to my, the answer from my diagram, I got it as 0.24. So yeah, this is correct. This is your 0.2 over here. Since, I got 0.24, I'm going to write 0.24 because the question says answer should be very close to 0.2 and never exactly equal to. That's why I will not round up my answer to match with the given value. I'll use whatever I got from my answer. Is this clear, Amir?
Yes, teacher.
Okay, now there's a problem. This one will only give you, sometimes this one will score you 0, like this entire working will actually score 0. Why? Can you tell me? Why would this diagram would actually score 0?
You can repeat the question.
Yeah, I was asking that why, I mean, this diagram matches with your given questions and everything, na? But still, this will give you a 0 mark, or this type of answer will get 0 marks. Why do you think that this one will that might get 0 marks?
Um, I didn't use the provided space.
Yeah, you didn't use the provided space, right? This much area was still blank. That means you did not use the provided space, so obviously they are going to cut marks for that. And that's why you should use always the maximum length as you can. So over here, maybe I should have drawn the graph something not like this, but maybe a little tilted. Like I can create this entirely. I do not actually have the option for rotate this. Do I have it now? Create striker, redefine. No, I don't have the option to rotate this. But if I would, tilt this and draw this from the vertical plane, then that would have, no, that would also not use 70% of the area. I will have to increase the length. I'll have to use like 9.6 and 14 centimeters, which I was previously using. Then it would have created or used 70% of the area. But yeah, I mean, since I was working in a PDF, I had to minimize the length to fit my scale and everything. But otherwise, you got the idea, right? Amir, is this clear to you, the parallelogram and the vector diagrams?
Yes, teacher.
Okay. Then if you move forward, they're asking that state the principle of conservation of linear momentum. Same thing. Now, can you tell me the answer for this question?
Moments before is equal to after collision.
Hmm. And this is 1 mark. They're giving you 2 marks for it.
There's no resultant force, no?
No, no, not having a resultant force means that is another state to describe equilibrium state. Okay,
Mm.
like when they ask you that define equilibrium, then you're going to write both the answer that okay, resultant force is zero and your total moment is equals to zero, right? Not for momentum, sorry. Yeah, for momentum you're supposed to write that provided that no external energy acts onto the system or no external force acts onto the system. Right. Only if the particles are colliding with each other, whatever force the particles are providing to each other, that is only force act during the system. Like external force as in friction, air resistance is not a part of your calculation. Is this clear?
Yes, teacher.
That's why, over here it was written that yes, total momentum before and after collision is same, but your no external force acts onto the system, right? No external force acting onto the system means that there will be no external force as in friction or air resistance acting over here for the entire process. So then over here, calculate the initial velocity of sphere P. Mass of sphere P is this much. Yeah, I mean, initial velocity of sphere P, right? Mass of sphere P is given. So don't we know that your total momentum before collision is equals to total momentum after collision, right? Before collision, only P has motion, Q was stationary, so there is no actually momentum for Q. So even if I do not know the mass of momentum for Q, that will not be a matter for me. And again over here, total momentum before collision of P is what? 0.12, obviously with the V, plus 0, and then after collision 96 and 0.14. From there, you just make V the subject. It's going to be 0.096 plus 0.14 over 0.12. How much do we get from here?
1.96.
1.96, 1.96 then. Right, that's your velocity. Okay, now we're done with this question. Amir, are you available tomorrow around 2 p.m. again? Because I won't be able to finish this in today's class. We'll need another class to finish this last. Oh,
Tomorrow, 2 p.m. I have school.
oh, okay, yeah, tomorrow you have school, yeah. Just 1 minute. Is it possible at 10 a.m.? Are you available?
10 a.m.
Do you have class?
Tomorrow was Sunday, no? Yeah, I
Yeah.
have a class.
Acha, in that case, can we extend today's class a little bit? That way I will finish this and then, you can just move on to your worksheet.
Okay.
Okay. Then we'll quickly finish this. Okay. Now, this one over here is a little tricky. Not that much because this one just gives you an information, and I think then, yeah, Newton's laws of motion. Newton's laws of motion, like forces, that is a concept. They're going to match this with your momentum, they're going to match this with your energy, they're going to match that with your moment also. So Newton's laws of motion is very important because they don't ask you that separately, they ask you that is a combination for moment, momentum, and what was the thing? Energy, right? So over here, they're saying that a spaceship is used to make astronauts and equipment into the like is used to take astronauts and equipments to the International Space Station, and these spaceships contain a orbital module, a descent module, and a service module. Okay, so this is orbital. In the middle, you have your descent, and the final, you have your service module, as shown in the figure. The astronaut returned to Earth in the descent module. Like only this one actually returns to the Earth. The service and orbital maybe gets lost during the process. Before entering the Earth's atmosphere, the modules all separate. The orbital module O and service module S move away from the descent module D in opposite direction as shown, and determine the velocity of V of the descent module after separation. Okay, I need to find out the velocity of this after the separation. All of their masses are given, and this one's velocities are given, right? First thing, what is their velocities before collision? This is actually not a collision theory. This is an explosion theory, right? Before explosion, they were all combined, and if their initial velocities are not given, that means we are going to assume that initially this ISS before entering the Earth's atmosphere was stationary. Okay, that's why the initial velocity is stationary, and their journey starts when they starts to explode when S and D moves in opposite direction, S and O moves in opposite direction, then D. Okay, as the first thing to understand, if D is falling on the earth and this is earth, I understand that, why O moves in this direction, because if O moves in this direction, it will provide a downward force on D that will cause the descent module to move towards that Earth's atmosphere now. But why does S moves in this direction? Can you tell me? I mean, not quite related to this question, but if O is moving in the upward direction, we are considering this is where Earth is, okay, on the right hand side. So if O moves away from the atmosphere, that means obviously O will push on D. Because of this pushing force, D have now a force acting in the direction of Earth. So using this, D can actually move down to the Earth, right? So O moving away from D kind of pushes D towards the Earth. That's a beneficial thing. But why is S moving in this direction compared to D? What does this has to do with the motion of D? Amir, do you understand my question?
No, I don't understand this question. Answer, thanks. I'm reading
Again,
it.
I'm telling you, I'm explaining this to you 1 minute. You think of this way, this is Earth, right? In order for the astronaut to reach the Earth, what was the phenomenon happening? The astronaut was in the D section, right? And the orbital was over here. When the orbital moves in this direction, that means what? If the orbital is moving in this direction, obviously it will push D in the downward direction, right? So the orbital section moving against gravity or against the atmosphere kind of pushes the descent module towards the atmosphere, which will obviously work in a favor for the descent module, right? Because the orbital module provides the descent module with a downward direction. With this push, the descent module will be entering the Earth's atmosphere and like, move in the downward direction. Is this clear?
Yes, teacher.
There's a benefit, right? If the orbital module is moving against the gravity, it acts as a benefit for the descent module to move towards the Earth's atmosphere. But why is moving in the downward direction? Can you tell me? I
Due
mean,
to gravity.
no, due to no, no, no. This thing separates before entering gravity. Okay, like how O separating from D pushes D in the downward direction in favor of what I want, but how S is moving away from D in the same direction will create any effect. Like we understand that okay, when orbital section was moving away, D was moving down. That kind of works in my favor. But what is the
So
problem?
it
S is
already has a speed.
yes. Again, can tell me what is that?
It already has a velocity now, so it'll when it separates, so S will move down.
No, not that. Problem is that when O moves in the upward direction, it gives D a very big velocity. Now, with that velocity, if D enters the Earth's atmosphere, that entire module will catch on fire. We don't want that, right? So I need to like decelerate that descent module. I need to make that descent module enter the Earth's atmosphere at a smaller velocity. That's why when S separates, S also provides a small upward force on the descent module, right? So that way, eventually the descent module will be able to enter the Earth's atmosphere without a very high speed, without causing any damage to the descent module. Is this clear?
Yes, teacher.
Right, again, this was not quite related to the question, but quite a interesting thing over here. Now they're asking that what is the total momentum? So determine the velocity of this descent module after the separation. I know it's going to be zero initially. After collision, what do we have? Mass of O is 1350 times 0.82. This is the momentum of O. O was moving in the against, like, O is the only one moving up in the upward direction. D and S will move in the downward direction. I understand that now. So I'm going to write again over here. They're asking for velocity. They could have easily asked for speed, which is a magnitude version. They're asking for velocity. That means I have to work with your direction also. They did not mention, in which direction D will move. Using the understanding what I gave you previously, using that you have to identify in which direction D is going to move. So from here, I understand, because of the pushing force from O, or also the pushing upward force from S, D would still fall in the downward direction. So we have your 2950 V plus S is also moving in the downward direction, 2100 times 58, right? And from there, you just make V the subject. So you just make V the subject, and that's going to be 132950. How much is this? Oh wait, I think I made a mistake. If I get, yeah, it's supposed to be 3-1. This one will be negative. This one will be positive after the subject change. Sorry. Then calculate this and let me know the value for your velocity.
0.78.
0.78. Okay. Then that's your velocity, 0.78 over here. Wait, 0.78. Oh, my mistake. Sorry, sorry. You're supposed to like subtract this. When you take this to the right hand side, it becomes negative. You're supposed to get 0.0376. Hmm. But I can see every data was given in like, two significant figure. So I'll write like 0.38. Better to write 0.4, because it's such a big data than if you write 0.38. So then that's it over here. We got your velocity. Moving down, they're asking The velocity of the descent module can be changed by using a rocket motor, and the rocket motor ejects hot gases at high velocity. Explain how velocity of the descent module changes when the rocket motor is used, and you should refer to Newton's laws of motion. Can you identify like what is happening? Like, without the rocket motor, the descent module is not does not have any motor, right? That's why whatever the forces the descent module gets from the orbital section or that like S section, right? Using them only, the descent module can change its like modify its velocity. But after S and O separates from D, D cannot change its velocity, right? Whatever velocity, because of this moving away from D, whatever it gets, that's the velocity. It's going to stay at that only. But if I fit in a motor with the descent module, then I can like modify my speed on my own without depending on O and S. Now they're saying that why exactly this rocket can create this modifying velocity effect for the descent module on the descent module. And they have also given information. This rocket basically what it does is that it ejects hot gas in the opposite direction at higher velocity. And using this process, somehow the rocket motor will be able to modify the velocities for the descent module. Right. So you need to identify the laws of motion over here. Do you understand the question so far, Amir?
Yes.
So what do you think the answer will be?
So it reduces the velocity, no?
Mm-hmm.
So when it exerts a force downwards, the
First, try to identify, like draw a scenario of this, right? This is your descent module and this is your rocket over here. Right? In this case, the descent module is, let's say the descent module is supposed to travel in this direction. What is the rocket module doing? It's going to eject hot gases at higher velocity in this direction. Now, so what happens is that when this, what is this called? This rocket is ejecting gas in the opposite direction to its motion. Right. The motor provides a force on this direction for the gas molecules. The gas molecules provide this direction on the motor. Since the motor is fitted inside the descent module, so the force from the gas actually acts on the entire descent module. Now, so because of this force, what? There's an external force. A force means it has an acceleration. Acceleration means there will be a change in velocity, right? And the idea of the motor providing a force on the gas providing a force of equal and opposite magnitude on the descent module, that is your Newton's third law. Okay. And because whatever the gas is providing a force on the descent module, that is the only force acting on the descent module, right? Other than this, after S and O have separated, there was no other force acting on descent module. Na? So whatever the gas is provided a force on the descent module, that becomes your resultant force. And resultant force means this is your Newton's second law. This is how you're supposed to think for these questions. Is this clear, Amir?
yes, teacher.
You struggle with forces also too, right?
L-
No, because I remember you said that you are struggling with momentum, work energy, power, and the topic too now. But I can see that your forces concepts are also not very clear. So we need to take classes for forces also because So what do you think? Like, you think you're okay with forces or what?
I think I'm not.
Yeah, but I
I
also
forgot.
think,
Please don't.
yeah, okay. Also, did you sat for any exams in Jan?
No.
Okay. Then 1 minute. The rocket motor exerts force on that, hot gases, and according to Newton's third law, okay, I'm just going to write in short, N3. According to Newton's third law, according to Newton's third law, hot gases exert equal and opposite force on rocket module, which acts as a resultant force. I'll just write RF, which acts as a resultant force on descent module. Okay, and then I'm going to write that which acts as a RF on descent module, and then we will write that from Newton's second law N2 for resultant force there will be acceleration which causes change in velocity. Okay, you know how I have used so many symbols in this answer, N2, N3, RF, A, delta V. You cannot use them in your answer. Okay, make sure you write them in detailed word. Is this clear? Do you understand all these symbols over here?
Yes, I got it.
Okay, then. Right. After this, they're asking when the rocket motor is operating and the velocity of the descent model changes by this much over a time of this second, and the mass was given, we need to calculate the average force. Can you do this as a classwork right now? Sorry, 1 minute. This was the question.
342 newtons.
142 newtons, right. How did you calculate that?
I found the force, I mean the momentum.
Okay, and then divided by time, you got your force, right? Or you could have easily used easy process m delta v over t, right? This was your delta v, this was your time, this was your mass. Same process, you eventually going to get the same answer, but this would have been a less time consuming process. Is this clear?
Yes, teacher.
Okay, now we get 342 Newton. That's fine. We're going to write this in the given space. We actually have less like, okay, they're saying a skittle is a wooden object that can stand upright on one end. Okay, this is a skittle that can upright on this end and then this end, right? In a game of skittles, a ball is thrown at some skittles to knock them over, as shown. And the diagram below shows how the ball just before it collides with the skittle. I can understand the ball was moving towards the skittle. The skittle is not moving, right? So skittle is stationary. Ball is moving towards the skittle. If you move down, it shows the graph shows how the velocity of the skittle varies with time. The time shown on the graph starts just before the ball hits the skittle, right? So I can see that exactly maybe from here, that is how much? 14 seconds. From 14 seconds to roughly here, that is 48 seconds. Okay, this is 48 and this is 14. So this is the time for which the ball was in contact with the skittle. After that, they lose contact, and that's when you reach a constant velocity. Okay, before 14 you have a constant velocity of 0, means before the ball hit that skittle, the skittle was basically motionless. That's why it has a 0 velocity. And then again after 48, what did you saw is that after 48, you have a horizontal line indicating you don't have any motion after 48, right? So you get nothing after that. And so then over here, yeah, right. That's what we can understand from the graph so far. After this, if we move, determine the average velocity of the skittle during this collision. So average velocity means I understand that velocity is only acceleration is only occurring for this slant section, right? So I'll talk about the linear part of the slant section. And then again, how can I identify the linear part of the slant section? I can use a scale, and I'm going to identify exactly from which point the what is this line starts to curve, right? I can see this one and exactly this one, like at 20 and sorry, so I'll have to remove the scale. At 20 and at 46.
46.
Yeah, 46. And another thing, you cannot draw solid lines on your graph if that is not a part of your graph. If you're taking reading from the graph, you always have to draw that as broken line. So that's 20. And over here, I should write this as 46 because 46, I'm going to use that, but it's not written on my axis, so I have to write down the value. Huh? So this is 46 and 20. So this is your change in what x-axis you got, and change in y-axis is going to be, how much is this? 0.2 and 2.9, no 8, 2.8. So we have coordinates like 0.2 at 14, 2.8 at 46. So you can easily find your acceleration as it's the gradient. So you just calculate the equation for the gradient VU over change in time. That's your 2.8 minus 0.2 over 46 minus 14. And then you calculate this. Amir, can you please calculate this for me?
0.08.
008 meters per second squared then. Okay. Acha. After this, they are saying that we need to use Newton's second and third law of motion applied for this, ball and the skittle during the collision. Yeah, I mean, This is your same process, every time. Again, over here, they're giving 6 marks for it. I think in the previous part of the same worksheet, they were giving like 3 marks, 4 marks for it, right? The basic idea is that during the collision, they provide equal and opposite force on each other according to Newton's third law, right? And yeah, according to Newton's third law. And then you talk about your Newton's second law. Now, Newton's second law is acting differently for the ball and the skittle. For the ball, what is happening is that initially the ball was moving to the right hand side. Okay, sorry, initially the ball was moving to the left hand side. During the collision, the skittle obviously provides a force on the ball in this direction, right? This is the resultant force that will act on the ball because of the collision. Now, this resultant force is against the initial direction of motion. So, whenever I provide a resultant force on any object that is against its direction of motion, it will have two options to follow. It will either, decelerate and move in the same direction with a smaller velocity, or it will reverse its direction and move with the velocity in the opposite direction. Okay, so I do not know what will happen for the ball, but I only know at least the ball will decelerate. Okay, but if the ball will is a like if the force that is exerted on the ball will be enough to reverse its direction or not, I don't know that, but I know that yes, it will decelerate because the resultant force that will act on the ball was actually against its initial direction of motion. So according to Newton's second law, this resultant force, which is kind of acting like a resistive force this time, will cause the ball to decelerate. I know at least this much. And for the skittle, what will happen? During the collision, the skittle initially was before the collision was at rest. So during the collision, a force was exerted on the skittle by the ball, and that force will be over here. Now, since the skittle doesn't have anything to carry from the before collision part, right? It didn't had any velocity. So whatever force acts onto the skittle, that becomes is the resultant force. And if there is a resultant force, obviously the skittle will accelerate to the left with a velocity of 0.08, means with an acceleration of 0.08 meters per second square. So for this skittle, I can guarantee you that it will move to the to the left hand side. But what will happen to the ball? We don't know that. Without any calculation, we cannot give you the fate of the ball's movement. That's why we are going to write that okay, the ball will decelerate, but will not mention in which direction, or will not mention the direction. Is this clear?
Yes, teacher.
Okay, so now for 6 more questions, I always design the answers in two portions. 3 marks for ball, 3 marks for the skittle. So first thing, the first mark is actually given for both the particles. For both the particle means I'm going to write it in this way that during collision, the ball and the skittle exert equal and opposite force on each other. And during collision, the ball and the skittle During collision, the ball and the skittle exert equal and opposite force on each other, and equal and opposite force on each other from Newton's third law. Okay, you just write that from N3. That is 1 mark. Okay, then we're going to focus for ball in one paragraph and skittle in one paragraph. So you're going to write that for the ball, the force exerted by skittle is against its initial direction of motion. Its initial direction of motion according to Newton's second law. will cause the ball to decelerate, right? I'm not going to mention, in which direction it will move or not, move and all. I will not mention anything because I don't know. So I'll just say it will decelerate. And then for the skittle will move. Acting on it. So from N2, see how I'm mentioning that how the skittle will move to the left and not mentioning in which direction the ball will move. We don't know that, right? This is your final answer. Is this clear?
Yes, teacher.
Right. Okay. Another thing, for your star mark questions, I always create scenario. Like, how in one paragraph, I'm only focusing on ball. In another paragraph, I'm only focusing on schedule. And it's connecting at the top. Right. So this is how you create your star mark question. In some talk about at least two, three particles. Okay. So for those two, three particles, you first decide, who is moving to which particle. So which particle is you're starting from? As we're talking about during collision, so we first talk about what are the forces acting for the two particles during collision. Then we talk about individually. Since the ball was moving towards the skittle, that's why we talk about the ball first and then the skittle. Is this clear?
Yes, teacher.
Right. So with practice, you can actually identify how to arrange the answer and write them in a logical sense. Right. So this requires a lot of practice. Then if you move on to this one, they're asking that the ball is thrown again and collides with another stationary skittle. During this collision, the horizontal velocity of the ball changes from 7.2 to 1.6. Now they're saying that after the collision, it decelerates its velocity but continued to move to the left. That's why it has a velocity of 1.6, okay? Not minus 1.6. Minus would have indicated the ball would reverse its direction. So if you have plus 1.6 indicating that there is no reverse, the ball is continue to move to the left hand side. And the horizontal velocity of the skittle after the collision was 3.1 because obviously before collision, skittle didn't have any motion, right? It was stationary there and in the same direction as the ball. Okay, we need to determine the mass of the ball. Okay, mass of the skittle was given. This is the scenario. Before collision, this is the skittle, this is the ball. This one was moving at a velocity of 7.2 in this direction with a mass of 1.4 kg. This one has a mass of m kg and this one was at zero velocity. After collision, what happens? The skittle and the ball are now moving in this direction. This one's velocity is given as 3.1 meters per second now with an m kg, which I have to calculate. And this is at 1.6 meters per second with 1.4 kg. Right. Even though, after collision, they are traveling in the same direction, but they're not connected over here. They're separate from each other. I can see that everyone is moving to the left hand side. So there's no point of writing left is positive, right is negative over here. We'll just write this total momentum before collision is your total momentum after collision. Before collision, we don't have anything for S, so I'll write 0 for that. 0 plus 7.2 times 1.4. And this one will be, this is going to be M. 3.1, right? If you calculate, you'll get your answer. How much do we get from here, Amir? Sorry, 1 minute.
2.52.
2.52, okay. 2.52, or we can write 2.5 kg because the other particle's mass was given as too significant figure. So we'll stick to 2.5. Is this clear now?
Yes, teacher.
Okay, in that case, we are done with momentum.